Hello everyone and welcome back to the channel. Today's lesson is about resistors in parallel and a very important current division rule. Let's dive in. Let's consider two resistors, as you can see here, R1 and R2, connected in parallel with a common voltage across them that we call it as voltage V. From the Ohm's law, we know that if I want to find V is equal to I1 times R1, which is in that case is equal to I2 R2. Okay, solving for these currents, what I1 is giving me, I1 is V over R1, and I2 is going to be V over R2. Now let's apply KCL at the top node over here. If I apply KCL, I can write I is entering to this node, while I1 and I2 are leaving the node. So therefore, I can say that I is equal to I1 plus I2. Substituting I1 and I2 with the value that we had is make I is equal to V over R1 plus V over R2. Or I can take the common factor of V, which is equal to 1 R1 plus 1 R2. So this also can be written as I is equal to V over R equivalent. So therefore we can say that what if we compare these two, we can say 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So if you want to solve for R equivalent, what we can say? We can say that 1 R equivalent, we can say that the common denominator, is equal to R1, R2. Here we have R2 plus R1. But what is R equivalent? R equivalent can be written as R product of R1, R2 over R1 plus R2. This formula gives the equivalent resistance of two resistors in parallel. For L resistors in parallel, the formula can be written as 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 up to plus 1 over Rn. Sometimes it is easier to use the conductance where G is equal to 1 over R. Then the equivalent conductance is just the sum of those conductance. So G equivalent is equal to G1 plus G2 plus Gn. Now let's find how the current divided between the resistors. We already know that the total current was I, which is equal to I1 plus I2. Since each branch has the same voltage V, and we find that V is equivalent to IR equivalent over here, what we can say from here, we can say that V is equal to IR equivalent. From everything, we can find the I1. So what is I1? We find that, let's go here. I1 is V over R1. But what is V? From here, we can find V is equal to I R equivalent. But what is R equivalent? It's going to be I times R equivalent is R product of R1, R2 over R1 plus R2. Okay. If rather than V, I replace with this one, I can say that I1 is I times R1, R2 over R1 plus R2 times, over, this is my I1, over R1. So, solving for, rearranging everything and solving for this one, R1 and R1 cancelling each other, rearranging this one, I1 is equal to R2 over R1 plus R2 times I. If I do the same thing for I2, I will get R1 over R1 plus R2 times I. These two called as current division rule, which is extremely important to solve the problem. The current through one resistor is proportional to the resistance of the other branch. The higher the resistance is one branch, the lower the current in that branch. So, which is very useful. Let's now see extreme cases. We have two extreme cases. Assume that when two resistors are in parallel, the first extreme case is when one of the resistors is equal to 0. So, in that case, we have a short circuit for this resistor. And what is happening if you have the short circuit? R2 is becoming 0. Then what is happening? So here we have I1 and I2. What's happened to I1 and I2? So if R2 is equal to 0, then no current pass through I1, and therefore I1 is equal to 0, and all the current passing through I2. Therefore I is equal to I2, and we have short circuited. The value of the equivalent resistor that we show R equivalent is equal to 0. R1 is also short circuit. Another scenario is when you have the open circuit. Let's assume that your second resistor has a very large number that we say that it is like open circuit. So in that case, what is happening to my I1 and I2? I2 is going to be equal to 0, no current flow from this resistor. Therefore, all the current must pass from resistor 1. Therefore, I, the I1 is equal to I, total current passing through I1. In that case, my R equivalent is going to be equal to R1. So these special cases are very important in practical circuits that we will see with few examples that I'm going to solve in the next two videos. That's wrapped us our discussion on resistors in parallel and the current division rule. If this video helped you, please give it a like, subscribe, and hit the bell icon so you don't miss future lessons. A question or thoughts? Drop them in the comments below. Thanks for watching and see you in the next video.